happy to have Rifath from Stanford, who will tell us about target space boundary terms from the worldsheet.
Hi, let me write one question first. Right, so there's actions that sort of you know how to derive from string theory, string field theory. But before that, let's say like this is the action for metric derivative field on some manifold. And if the manifold has boundaries, then to have a well-defined variation principle, you would need to sort of add some boundary terms so that the delta I would be 0. When you impose the equation of motion and the boundary conditions. For dirichlet boundary conditions, this is a action which has well-defined variation principle. Now, so first let's focus on this part. So that where does this action comes from some sort of a derivation in string theory. Now, in usual examples of on-shelf. Usual string theory that is there in Worldsheet book. What happens is that basically you have a worldsheet and the worldsheet is embedded in the target space-time. Target space-time is this d-dimensional coordinates in which you embed a two-dimensional worldsheet, and then you do a path integral of over the embeddings of that worldsheet on the target space-time, weighted with some action on the worldsheet. Now when you do this, you also integrate over the metric on the worldsheet. And now you the gauge symmetries of the worldsheet as the diff and the y, and since y symmetry is a gauge symmetry, it should not be broken even at the quantum level. So you demand the beta functions on the worldsheets to be 0, and that constrains your target space-time fields, and that comes out as equations of motions for target space-time fields. And so from conventional string theory, what you first get is the equation of motion for target space-time fields, and from it you infer an action. But you could have inferred more than one actions because that two different functions can share the same stationary points. And yeah, but this is what you first get from the calculation. But now then you ask the question whether can you get the action directly from string theory, and yes, the answer is yes, because you know how to compute amplitudes. So in on-shelf string theory you also get amplitudes in target space-time, and from but those are on-shelf amplitudes. And then string field theory takes the following approach. You first S matrix is nothing but what? Just endpoint connected correlation functions with amputations of the external legs and taking them on shell. Those are your on-shell amplitudes. So first from on-shell amplitudes, you extend it to off-shell amplitudes. With the criteria that however you extend, when you go back on-shell, it has to match with this. And whatever ambiguities come up in this particular process, has to be equivalent in the sense that I was saying. And from off-shell amplitudes, you reverse equivalent to what? It must be equal to each other. I'll make it precise in the next time. So there'll be some ambiguities over here, which we'll keep aside for a second. Now from off-shell amplitudes, you reverse construct the action. Because if you knew the action, you do Feynman rules and you will construct all the endpoint correlation functions and you can construct the off-shell amplitudes. And now you know this, you reverse construct the action. So in that sense, it's better than this because now you are landing at one particular action from this one. And then there's no other ambiguity action. But remember, there was an ambiguity over here. And that ambiguity roughly boils down to like something called local quantities which you have to choose. But all of that ambiguity is nothing but target space and field redefinitions of this. It's not fully proven, but proven in some context, but that is what the belief is. So what is target space and field redefinitions? Now the target space has fields, metric, electron, and all the kind of fields. You just mix them up. That's it. So you can write down the action as a function of R and phi, or you can write down action as a function of R tilde, G tilde, and metric G tilde and phi tilde, where G tilde and phi tilde are written in terms of G and phi in some mixed way. Okay. Now there is another approach to offshore string theory, and that is called the nonlinear sigma model approach, pioneered by Franklin and Setlin. That is what I'll be talking about today. Not talking about the approach, but I'll use the approach to do something. And that approach is nothing but roughly it is one thing that you get from that approach is that you get this action directly from a computation of some quantity, and that quantity is the sphere partition function. Now the tree level action basically comes from a sphere partition function. I'll make write an equation for this more precisely later. But then again there is also an ambiguity over here, and then we'll also talk about what that ambiguity is. I'll just mention what that ambiguity is. Okay, so you get so Setlin basically what he did was that he showed like this roughly. There's a prescription which I'll say a bit more. There's something called some epsilon. Don't think what epsilon is. Hidden in the sphere partition function is the action for the target space-time field in a particular way. Okay. So using this, which I'll say later, Setlin basically derived these guys. Okay. So today's question is, can you write out a computation in which the boundary terms also comes out of a computation in the same using the same methods in which the bulk terms came out of a computation in the nonlinear sigma model approach. So that's what today's topic is going to be about. Okay.
I think I'm a little confused. Once you have the bulk terms in the action, aren't the boundary terms completely?
Yeah, determined. Yes. So it's like
it's just cool that you can get it all.
Yeah,
That's it. There's no ambiguity that's being solved by this.
Yeah, exactly. That's it. It's like we put these given nothing added these terms by hand to the action input action to make the ratio principle well defined. Now, is there some computation that spits this out?
I mean, which boundary terms we add depends on which boundary conditions we want to impose.
Correct. So
there is an unresolvable choice that has to just be made.
Exactly. So I'll be doing the initial boundary condition, but I'll say a bit more.
And you have that choice as well in this method, so you could have gotten.
Yes, you have a choice to impose boundary conditions, but it's a bit unclear why exactly the sign that we're choosing is imposing that boundary condition. So that's something I'll say that. Okay, so now let's start. Oh, before we start, so this work is done with my collaborators Ahmed and Shoaib, who are sitting over here. So so this paper, you know what's the archive? Archive number of the paper.
I think we can look at that.
That's fine. First paper which was written with Ahmed was basically for the dilaton case. We also derived this and this. This is the term that Setlin puts by hand, but it comes out of a computation for us. And in the next paper, with Shoaib and Ahmed, we derive this whole thing. Up to, you see that this is in leading or an alpha prime. And it's not like we derive the whole thing, we also derive this whole thing in linear order in the perturbation. What perturbation also is? Perturbation, basically perturbation of the target space-time fields around a particular background. Okay. Simplest thing that we could first do is what we're doing. So today I'll present the setup, the logic, the calculation, and I'll present the calculation for the dilaton, which is just a two-step calculation. When it condensed, it became a two-step calculation. Now for metric, the challenge is bigger. That I'll just state what results we have, and maybe he can maybe give a talk in the future. All right. So let's start. Share all this. Enough. Let me introduce or talk about sentence prescription. So a bit of history also. That was done by Franklin Setner, and then there was this ambiguity. There's some ambiguity over here, and because that ambiguity is basically breaking conformal invariance on the worldsheet, something which is very bad to do, and so a lot of people don't take it seriously. And then there is this work by Aaron and Amel in Offshore Strings Part 1 and Part 2, where they sort of made sense of Setner's work and why it is okay to do many things and stuff like that. And then there's also this work, they extended Setner's prescription was leading on alpha prime. They extended the prescription to all orders in alpha prime, but still for the massless sector, not for the massive sector. And then there's another work by Aaron Ammer and Alex, who extended this prescription to all orders in alpha prime and for all the massive sectors also. And they wrote down an action for closed strings, and in some way I think that work is very good. Okay. So we are going to take the naivest prescription and we are going to use it in a particular way. Okay, so let me tell you what is the original Setner's prescription. Before that, let me tell you something. So in on-shell string theory, how is the partition function of the sphere defined? Basically, you take a sphere, embedded it on the target space-time, where you integrate the embedding fields, which have become scalar fields on the worldsheet, and also the metric on the worldsheet. And now this has a y cross diff symmetry, so you mod it out by the diff cross y symmetry, and in the end you get a function of only the target space-time quantities. Let's say on a sphere. So this is a sphere partition function. In offshore string theory, what you are going to do in Setner's offshore string theory is the following. You're not going to integrate over the conformal mode of the metric. You can take a metric and write it as e cross to omega times. So the conformal factor and the conformal part of the metric, and you're only going to integrate over the conformal class of the metric. No more y symmetry. Only going to mod it out by the diff, weighted with the same action. Same thing. So now, as a result, this quantity will also depend on the conformal factor. So the left hand side also depends on the conformal factor. And this was a CFT, or at least you're going to restrict your field theory couplings, which is G and phi, which is the same thing as the target space-time fields, to be those configurations for which this becomes a CFT, is still a CFT. Here you're not going to do that. One reason is the following. First of all, if you want some quantity, like an action, it is a quantity of what? Which eats up arbitrary configurations of G and phi, right? So you want to be dealing with a quantity in which you can plug in arbitrary G and phi. To this entity you can't plug arbitrary G and phi because you are not going to break conformal invariance. To this entity you can plug in, but at the cost of having the left hand side depend on the conformal factor omega. Now since now it's no longer a CFT, it's a QFT, so you there will be whatever divergence are there, you regulate it, so that's also regulated. And we'll tell you what precise regulator that we'll be using. But for now, think of it like imagine that there's some parameter. Okay. So now this is the quantity that you will be looking at, and Setlin's prescription to extract the action is the following. First of all, do all the usual gauge fixing. Gauge fix the diffs, and then you will get something like this. Now the ghost always, like on a sphere, the moduli space is just like what is it called, the zero-dimensional thing. What is it called? The ghost will sort of decouple from the matter partition function. So this will still remain a CFT, will not depend on the GN phi. No need to put any error on this. But this we need to put a error on this. So the sentence prescription is the following. In the matter partition function, there will be divergences first of all. Now the divergences will be of all different sorts. Polynomial divergences, logarithmic divergences, all different things. Now they say that the polynomial divergences all are non-universal because like this will be proportional to some finite terms, some infinite terms, and some logarithmic divergences. Now, throw away all of the polynomial divergences because they are not universal, and they can be changed to whatever you want under a different RG scheme. But the coefficient of the logarithmic divergence is universal, and that is exactly the action for the target space set fields, and this is the sentence T1 prescription. Fine. So you take the offset partition function, define it in this particular way, and extract the logarithmic divergence, and the coefficient of logarithmic divergence you will find setting the action for the target space time field. That is the prescription, and that is what was used to derive this. Okay. Any questions so far? Pardon?
The universal fantasy dependent format.
Okay, so this everything depends on omega. Good. So now, for different choices of different omega, you will get different actions. So the claim or what they showed in the Adams and Amber's paper in offshore string part 1, part 2 is that different choices of omega are nothing but field redefinitions of the target space time fields. Same story. Whatever ambiguity came over here are field redefinitions of target space time field. So you get different actions, but they are all related to each other by field redefinition. Similarly, here also there will be an ambiguity in omega, which will give you different actions. No worries, they are all equal to each other by a field redefinition of the target space time fields. And that's one proof, or mathematical proof, which I'm not going to say, but I'll give you a one-line argument. On the worldsheet, what are these target space time fields? On the worldsheet, they are coupling constants, right? So on the worldsheet, when you change omega, you're changing the scale on the worldsheet. It's like doing an RG. And when you do an RG on the worldsheet, what happens? The coupling constants change. And so meaning, what are the coupling constants? Target space time fields. So the partition function remains the same, the coupling constants change, the target space time changes. And so the new action as a function of the new field redefined target space time fields is equal to the old action as a function of the previous target space time fields. Just same argument in quantum field theory. The new partition function is equal to the old partition function with a different scale and different coupling constants. So that's what the one-line argument. So this is a okay. So is it clear what Setlin's prescription is? Because this is what we'll be using. Fine. Okay. Now we'll go to manifolds with boundaries.
So omega shows up in I as an extra field.
So omega was over here. Remember, it depended on omega.
Yeah.
So it depends as a function. This will depend on omega.
Yeah.
So this will also depend on omega.
Yeah.
So you fix one particular omega, do this calculation, you will get some function of. Now you look at it as a function of metric and phi. There will be some functional form. For different omega, it will be a different functional form.
But in I, it's like a coupling constant or it's like a dynamical field?
No. In I, the metric and phi are the coupling constants. Omega is some.
Well, metric and phi are like fields.
The metric and phi are fields in the target space.
So I thought I is the target space actually.
I is the target space. Actually,
So in I, they're like dynamical fields.
In I, they're
Yes.
And on the worldsheet, it's coupling constant.
And omega in I is what?
It's something. It's just that.
It's not a dynamical field.
It's not a dynamical field.
It's just some like coupling constant sort of.
Don't know
Like a
the-
background or something like that.
It's some quantity sitting somewhere, which will probably mostly be integrated. You'll be doing integrals on the worldsheet. So depending on omega, the final answers for the integrals will all be different. But explicitly, you will see the metric and phi dependence in this quantity.
Like the equations of motion don't have varying omega.
No, they are not. Yes, exactly. You take this vary, you will not find omega sitting over there.
Yeah.
But for different choice of omega, you do this construction, you will still not find different the omega sitting over there, but the equations look different in terms of metric and phi. Okay. Sure. Maybe should I write down this? Right? Okay, now let's go to half space. Okay, now we're going to generalize this story to manifolds with boundaries. And the simplest manifold with boundary that we will be considering is the half space. Xt, this is all the other direction xi. So our manifold with boundary would be the positive this space, this half space where xt is positive, and this is null present. So then the first thing that we'll do is we will compute the sphere partition function on a background with half space, meaning same quantity, but now I'm going to put the restriction that xt is greater than or equal to 0. So what would this do? It will only, I'm only doing a path integral over the embeddings of the sphere on target space time, such that the embeddings is only on the right side of this wall. It cannot go and cross the wall. So this is a quantity that will compute, apply this prescription, and now find that in addition to the bulk terms, we'll also be getting boundary terms. And in defining this quantity, that's a choice that you have to make, and that choice we think is corresponds to the boundary condition, because that is exactly analogous to quantum field theory. I'll give that as an aside too. Okay. So now let me give you a theoretic aside. So I'll just draw a formula to calculate the one loop correction to the quantum effective action. So that's the quantum effective action and due h bar expansion. The term is action. Next term is the one loop correction to the quantum effective action, which is represented by this. That you can calculate with this. So this is a QFT statement. Algorithm string theory. If you want to know how to do this, I can say it. But it is. So what is this? On the left hand side is the one loop correction to the quantum effective action. On the right hand side, you're doing integrals, path integrals of world line, basically path integrals of embeddings of world line on the target space in a particular background that is provided by phi. How? If let's say this was a scalar field theory with in the Lagrangian the potential was u of phi. If you consider Lagrangian with the potential u of phi, then over here it would correspond to you embed do just standard undergrad quantum mechanics of particle propagators in a background potential v as a function of x and y, right? It's equal to u double prime of phi of x. That's it. That's the relation. So this is the QF relation. Notice that it looks a little bit analogous to the. Why? Because on the right hand side, you're computing world line path integral of world line embeddings. On the right hand side over here, you're computing path integral over worldsheet embeddings. On the left hand side is basically the one loop action to the quantum effective action. Here on the left hand side it is the action. Okay, this is the difference, right? So that formula is not exactly the same as this formula, but it's just same in spirit. So what we are all saying is that we'll just be inspired by what is happening over there and go with a similar story over here. Now there is a story to say for quantum field theory in box also. You can put your quantum fields in half space, and then you can apply Dirichlet boundary conditions over here. First in the path integral, and then calculate the quantum effective action, and then look at the one loop correction to the quantum effective action. And let's say that you have done that, and that is with Dirichlet boundary condition. That corresponds to using the same formula, but imposing Dirichlet and Neumann boundary conditions on the propagator. Meaning, you have your x, y, let's say here x comma y comma t. You have your taking all parts that goes like it bounces off, bounces twice, and all this kind of stuff. So that is the set of parts that you're going to include in this propagator. But now you can assign boundary conditions, and boundary condition is basically it is in this particular case assigned in the form as a choice of the sign of the bonds. Meaning, if the particle bounces off once, the contribution for that to the path integral is e to the power of the action. But the action is like the line integral of the Lagrangian from here to here and here to here, and plus either 0 or I pi, which is equivalent to either choosing plus or minus over here. So choosing this sign puts boundary makes this K satisfy boundary conditions, and then from that you can get this also which satisfies boundary conditions. Okay, and here there's a well we know what it means to be Dirichlet or Neumann in the propagator thing, because this is just a solution to the heat equation, and the boundary conditions that you're going to apply is that it becomes Dirac delta function when you take y and into x, and when y tends to the wall, the k has to be 0, that's Dirichlet, and when y tends to wall, the derivative of k with respect to y has to be 0, and that's Neumann, and that is achieved by imposing these signs in those kind of things. And so from this what we learn is that even over here when the worldsheet bounces off the wall, because you can consider contributions where there's a worldsheet like this. So let's say this is the wall. So the worldsheet could be sitting over here. This is a contribution to the path integral. Alternatively, another contribution to the path integral would be this. When worldsheet comes off, bounces off the wall. So the contribution for this is basically to the power of minus I nonlinear sigma model action integrated on the spin. Here it will be again e to the minus I. Now I would be the I of this guy plus I of this guy, because it's just the integral of the worldsheet which splits, but with the contribution from the bounds. So choosing that sign over there is where you impose, this is the only way to impose boundary condition. Or let me also say it like this. This is the only room for boundary condition basically. Once you impose this, that's it, you have defined this. And then what are you left with to do? Just apply prescription and you get one answer. So if you choose a different sign over here, your final answer that you will land in I will be different. So it could be this with different boundary terms corresponding to having a well-defined variational action principle for different boundary conditions. Okay. Now there is one difference between the particle case and over here. Over there, in the particle case, the minus sign corresponded to relationship boundary condition. Here, and the plus sign corresponded to normal boundary condition. In the string theory case, we will choose plus sign. And by direct analogy, we expected it to be Dirichlet, but we are getting it to be Dirichlet in both cases of electron and metric consistently. And again, let me say that first of all, this was an analogy. There was no reason to directly extrapolate it. It was an inspiration thing, and this is the end result, assuming our calculations are correct. Okay. So now let's now let me tell you how to. So in recap, so that's a certain prescription. And to get the target spectrum action, you need to calculate the Z matter. Now we define the Z matter as in a way that the Worldsheet is only embedded on the right side of the wall. It can bounce off the wall and do all sort of things, bounce n number of times too. And we're going to apply the settings prescription and find that boundary terms also come out of it. So the next thing is how to calculate this. So I'm going to say that next.
How long have the time passed?
We have like another 25 minutes.
Okay. Again, we all know if you want to do calculate k in half space, it's an undergrad problem to do it by method of images. Same thing over here. We can convert this to something else by using method of images. So what is Z half space? It has contributions from those embeddings which never touch the wall, but on the right side, plus those embeddings that bounces off the wall once, plus those embeddings that bounces off the wall twice and so many number of times. Let's say although you started with the manifold boundary which is half space and the left part was not even there to begin with. Now you're going to introduce the left part and take it to be the reflection of the right part. Introduce the left part and then also put, so initially the G and phi, the metric and the phi were defined only on the right side of the wall. Now you're going to introduce the left side of the wall, and define G and phi on the left side by just by reflection. And when you do that, and if you consider a contribution coming from a worldsheet which is on the right side, or you reflect this worldsheet to the left side, since the target specific fields are also reflected perfectly, mathematically this is equal to this, it is equal to this. So this quantity you can replace it by this plus half of this plus half of this. Similarly, here you have choice of either reflecting the bottom part or the top part. So you get two contributions in the extended space, in the reflected space, which mathematically just equates to this. And similarly for this also. Alright. So you can see that you have converted the half space partition function to a half of reflected space partition function. But now as a function of G tilde, phi tilde, and also same omega. Well, G tilde and phi tilde are basically now defined on the entire space, but on the left side is the reflection of the right side. In the data note paper, we just set G tilde or G to be delta mu nu. So and phi tilde was basically function of xi comma xt was now what? So phi there's a for the data there's a constant mode. That will be the same thing. That is what called as phi naught. Plus perturbations around the constant mode. Phi psi comma xt. Theta function of xt. So on the right side of the wall is the same thing. Plus on the left side of the wall minus xt. So on the left side of the wall is just a reflected part of the right side. So this is the perturbation. And the calculation done is basically to leading order in this perturbation also. For the most simplicity. And in the metric case, you perturb this thing and there's a calculation for that. And we'll find that it agrees with all of that terms to that order. But notice that the relative coefficient between the bulk and the boundary term is the most important factor that you have to get right. And that is indeed right. Okay, so now let me quickly go through this computation. So first of all, the way you do it is you take on the Worldsheet your fields XU on the Worldsheet. You're going to decompose it to 0 modes and non-zero modes. The y mu, which is a constant mode, is a function of z Worldsheet coordinates, constant mode plus root alpha prime times e. Then you measure dx roughly becomes dy times d eta. Now it starts looking more like a space-time integral. So this z half of z reflected space now becomes half integral. So this is in a back same thing. Dx, which becomes dvy integral d theta e to the power of minus I as a function of d0 phi theta. But for this very simple configuration, it will be I will have two parts. So this is the usual Polyakov action, the same thing as in the flat space, and this will be the perturbation V, which will be expanding. And the way you regulate this action is by inserting e to the power of minus epsilon lambda square over here, and that's the heat current regularization. Roughly what it does is that when you decompose this into the spherical harmonics, the higher and higher modes, which are the eigenvalues of the lambda square, they have negative eigenvalues. So e to the power of positive, it gets enhanced. So the higher and higher modes contributes more and more to the action, and it contributes less and less to the e to the power of minus action, and so this quantity converges in a particular way. So then rest is I think the concept is delivered. So rest is computation, and so the z half space now becomes integral d dy, and you have integral d eta times the e power of minus I, the integral d eta e power of minus I times e power of minus b, which you later expand 1 minus b plus order of b square. And then you make this into expectation values basically. Sorry, this was not that. Now you make this into expectation values. And then you introduce a normalization factor such that the expectation value of 1 would be 1. Okay. And it is this quantity that you compute. every calculation that I'm saying right now goes for the metric also. Yeah, for the metric, the calculation is just a little bit bigger. That's it. So, but okay. Now there is one thing that you have to pay attention to. Look at this P. Its expectation value of 5 tilde, right? So, okay, before the thing that you need to actually pay attention to, I'll just say the far wall region. Okay, actually, yes. So near the wall, since the railroad field is reflected, what happens is that it introduces a kink on the wall. Like if the, let's say this is XD, let's say this is the railroad perturbation phi, and if it was like this, and when you reflect this, what happens here? You get a kink. And because of this kink, you have to do some, what is it called? Certain things are non-zero, and that is essentially that is the source for the boundary terms. It is this kink that gives rise to boundary terms. Far away from the wall, the calculation is identical to what Septon did. What did he do? He just did the following. He computed this phi tilde. He Taylor expanded it as phi tilde of y. This is a function of like y mu plus root alpha prime eta mu. You Taylor expanded over here plus root alpha prime double mu tilde. So far away from the wall, it's as if there is no wall. The Worldsheet does not even see the wall. You far away from it, you just Taylor expand the data dot profile over here up to this particular point, and what you get is in the place of 1 point function. Now this is just 0 because it's an odd integral. Now over here you get expectation value of eta inserted at the same particular point, which is a divergent quantity. Here there's a divergence. In this is where you get log divergence. And when you extract roughly this goes as this. I write this slide. Eta mu at the same point z is equal to half delta mu omega. Where omega equals to summation omega equals to 1 into 1 This is a spherical harmonic expansion calculation, and you will get this thing. And now this by Euler-Maclaurin summation, the divergence would go as be a polynomial divergence and a logarithmic divergence. The logarithmic divergence coefficient is just 1. The lowest log x1. And so the over here you have integral over everything. So now you split this integral in far wall region and near wall region. The far wall's contribution to the z, which is the what we're going to call as z far, and from the z far you get the I bulk action. And the first thing that you derive that comes out to be this thing. And this is the computation identical to Septon's computation. Now what Septon does is that he does this, and after that he adds the additional term and then converts it to del phi square, which is the action that we want, and he leaves it over there. And now the term that he the total derivative term that he added, which is exactly the boundary term, Westo's theorem, is what comes out of computation from the near wall region. And in the near wall region, near to the wall, the profile of the dilaton is roughly this. This is a mod function near the wall because of the reflection. And because of this, the thing that you need to compute and insert over here, which is this thing becomes expectation value of delta plus many other terms that become 0 because of odd integrals, blah blah blah. The rest surviving thing is where this derivative is the right derivative, because that's the only thing that is defined. Notice that this quantity, you are not going to get it by Feynman rules. This is an expectation value of mod of something. And it's not like a 1 point function or 2 point function, the usual expectation value of 5 square, and all those kind of things. So you have to compute this fully. And we computed that in the appendix. And I'll just put the answer. This quantity is just root of pi, root of omega phi, root pi, where omega is that sum. Root of minus obviously, I will not explain to have the calculation being followed, just giving an idea of what the calculation will be. Okay, same thing. So, computed this, and now extract the logarithmic divergence. So, but before that, what if you at this particular point, if you look at the logarithmic divergence, it will be root log epsilon. That's not what you have to do. You have to integrate it on the xd, and then do an expand. Like what is it called? After you integrate it on the xd direction, you restore logarithmic divergence, and the coefficient of that logarithmic divergence which you get is what is I wall. This is minus alpha prime by 2. I have to say that all of the action that we are deriving is only proportional to the sphere partition function. So the final action is only proportional to that. But still, the relative coefficient between the bulk and the boundary term is what matters, and that is a derivation. But so I'm just going to write it equal to the and combining both of these terms, you get the total action, which is just the addition of these two things.
Which is there's an ambiguity in the coefficient of the log divergence? You're saying there's an ambiguity in the overall normalization of the action, right?
You mean the field definition ambiguity omega over that?
No, sorry, you were saying something about the coefficient is not fixed or something.
Oh yeah, okay. That is the thing. So the prescription is like Z matter is proportional to some overall, so it's equal to some overall number times this thing.
I see.
And in the coefficient of log epsilon is the action.
Yeah.
So this is what you get. So like this is never going to be fixed.
I see. I see. So that's it.
But in this, which comes out of coefficient, you need to get the delta factor right. Otherwise, you don't have a well-defined ratio principle. And that getting the delta factor is the whole point of the project. This thing. Okay. Yeah, and so from this, what you get is you get this and this term, which by integration parts just becomes del phi square. So sometimes when you talk about dilaton thing, people will imagine del phi square as the action. If you start with this as a bulk action, then obviously there is no boundary term. If you start with this as your bulk action, then obviously you have to put a boundary term, which makes it equal to that. Now, so in the cyclist computation, this is what you get first, and that was added by hand. And now that comes out of computation. Now for the metric case, you get all of this up to leading order in the. Okay, I erased it. Up to leading order in the perturbation. And that's pretty much it. That's the result. How many did that? Okay, that's it. Okay. Questions? Alright. Forgot to say future generations. But I'll first take questions.
Any questions?
Talk about the future dimensions.
Okay, now is this a derivation of given circuit term? I didn't say the metric case, but metric case goes identically and that will be a upcoming paper. Let's say assume that we no mistake has been made in the calculation. Then what to make of it? Like, so here's a prescription that people in 1980s or something used to derive this thing. Now we have used that prescription for half space. So there's a question whether what to do with this calculation. Another thing is okay, fine. This puzzle I would like to understand. This is not puzzle. Like I would like you to understand this analogy between the setlist prescription and this formula. Because perhaps that's a prescription in offshore string theory which will compute the one-to correction of the quantum effective action in terms of maybe some torus diagrams or something like that. And then that in the alpha prime zero limit must identically become the right hand side of that formula. And the left hand side should become the left hand of that formula. It must reduce to the QFT case. And then when it does, what to make of this sign? But so, is it like imposing boundary condition which corresponds to the choice of the sign in the bounds? Does it work out differently in different topologies or not? Don't know. Yeah, something like that. And then maybe calculate entropy or whatever.
Can you say a little bit about why this cyclic prescription works? Like, for example, why this gives the right equations of motion?
Well, that's the whole story by.
Yeah. Is there a simple way to understand that?
Okay, I will tell you my understanding.
Okay.
What are we doing?
Pull it out.
Okay, this is my tentative understanding, but I don't know if it's right or not. Okay, but something that I would like to see whether it works or not. What is this? This is bound to work. You are because what do you mean by you want an action to in string field theory? You want an action such that you use Feynman rules. You will recover all the amplitudes that you can calculate in string theory. This is reverse constructed from that, and so it is bound to work. It's like iteratively you define it. 3-point offshore amplitude is equal to the 3-point vertex over here. 4-point offshore amplitude is equal to 4-point vertex plus STU channels, and so the missing piece will be defined to be the 4-point vertex, and like that 5, 6, 7, 8, all that kind of stuff. And there's so what was the program? Extend onshore amplitudes to offshore amplitudes, and then in offshore amplitudes, whatever ambiguity was that, you show that it was derivation of a field differentiation, and then you went over here. Can you now do the following? Do extend. So here's a way in which you can extend the onshore amplitude to offshore amplitudes by this quantity. Now you insert some things over here, so that will some vertex operators over here, and so the offshore sphere partition function will give you those offshore amplitudes with an ambiguity omega, which is perhaps related to each other by field definition, and then that's it, right? Then after that, action is the generator of tree-level Feynman diagrams. The quantum effective action is the generator of 1PI diagram. Leading order is H bar, which is tree-level now. So you're bound to land on something which is the action only, because it is the generator. What's it called? Let me rephrase. Let's say suppose you do this all and it works out very well. So you are guaranteed that whatever quantity you write over here will reproduce all the amplitudes at the tree level. So now what is the generator of that action? So maybe that's the action. Maybe this is what they said in the part 1 part 2 paper or not, I don't know,
but why the log epsilon coefficient? That's the thing.
Okay, fine. So there's this story of conformal Killing group, which after you gauge fix the diffs alone, you are still left with y. In onshore string theory, it will be exactly like this times integral d omega divided by y, and that drops out. On the background, where this is the special backgrounds, then none of these quantities depends on the omega, so comes out of the integral and it drops out. Onshore string theory no longer, but the gauge fixing process is identical until that particular step. There's an alternate way to do that. That's also there. So over here now, you're left out with this formal thing that you still need to mod out, which is the volume of the conformity growth, which on the sphere is like infinite dimensional. And other torus or something else are finite dimensional, so you can just divide by it. Okay. Even another thing is that again it's there in the part of the program that it could be that now this is still a residual gauge symmetry that you still need to fix, and so there is these gauge orbits. And you have to not integrate over everything, but you have to only integrate over a slice, right? But let's say if you integrate over everything, even along the gauge orbits, you have to divide by the volume of the gauge orbits. But what would you do if the gauge orbits had different volumes? So it does have different volumes, and a proper way to do this procedure is take a derivative with respect to log epsilon, which is basically this thing. I said it in this particular way because this is what directly we're practically applying. Whereas when I state the description as minus del by del log epsilon z, which is how it is stated, then there's one additional step that I have not made people understand, so I don't know what to go into that. So that's roughly what this is. Yeah.
Any other questions?
You said you don't know how to get microcanonical relations.
So what?
Canonical relations. Somebody is for gravity.
Sorry, can you say that again?
Can you get microcanonical relations?
What is that?
Instead of fixing a metric.
Like normal.
Fixed map, yeah, non-boundary condition. Yes.
You can get those.
Maybe yes. I'll tell you what next to do. Okay. Yeah, so whenever it bounced, in particle case, whenever it bounced, I said choosing different sign corresponds to different boundary condition, right? Similarly, whenever the worldsheet bounced over here, the sign that we chose was plus, we call this answer. Now choose minus, you get a different answer, and that's not the calculation you have to do. Maybe we'll give you some that action which is a well-defined principle with respect to normal boundary condition. Maybe. In the particle case, it's very clear why these size corresponds to this. It comes up with definition. Here, we want to have some sort of an understanding of that. Yeah. And also we think this is it. This is the place where you can put boundary condition, because once you define this sign, that's it. You have defined the quantity, and assuming that sentence prescription works, then this is what you can do.
All right, let's thank Rifath.
I understand the drop rating technique but one thing it comes to have on this local horizon, how do you guarantee that somewhere behind the reason? And the reason why I say that is if you shoot from somewhere behind the horizon, because and like right upwards, eventually
I like when you guys each other things.
hopefully I don't know that it's not funny.
Are you guys doing for the weekend of the day?
Because you were
It's day 6. Yeah. Oh man, that's coming up so fast. Are you staying in the area?
I don't know.
I'll stay with one.
I think this is what you want.
I don't really like it.
I met someone today who does the community that's from LA. This is I guess on the other side.
Maybe
That was supposed to be black hole with nothing.
So my last time was with you actually.
Yeah, many of them
That
that was my first year, which I did. Hopefully not.
You guys haven't seen it.
Yes.
3 times. Physics program, applied physics.
It's there.
And you're- I think that's reasonable. And you download it.
I'm gonna publish.
Meaning you cannot take what's the mistake.
Yeah, like remember the
That doesn't mean that you cannot have
I got what was this?
Yeah, I think most of the time.
Okay, cool.
Yeah.
Oh, nice to meet you too. Okay, I'll be on the lookout. Because I was like, dang, if I feel like there was a people with your name on that, I would have noticed. Yeah, we'll post it soon. Cool.
So,
Yeah,
to talk to Rifath.
go for it. Go on. See you.
Today's Tuesday. There's a nice Mexican place, like an upscale Mexican place, it's quite good downtown.
I'll step in some place. That sounds good.
Yeah, and Kamal, that place is good.
Yeah, go on.
And we can't do Grand China.
Tuesday, yeah.
Yeah, where have you guys been going recently? I guess you went to Grand China last week. Where have you been going, Armin?
Well, I mean, with you, we went to Entire.
Oh, yeah.
That is another option.
That place is really good, yeah. Yeah, if you guys
But if it's less number of
Italian.
Yeah, so I guess time.
Yeah, this week we have to probably stay a little bit on the other side of this too.
just keep
But,
Oh, yeah, so it was more expensive.
but I mean, I think the only one that's like a little expensive is the Italian one, no?
Yeah, in time, come on.
Him is totally fine.
That bankrupt.
It was great, yeah. Yeah.
Yeah, anything else is like, I mean, Inta's certainly fine.
Yeah.
Even though it's very good.
Yeah, in Kamal is definitely fine. It's not that expensive.
Yeah.
Okay. You go to Worldsheet.
Carrying your shorts.
Okay. Oh, so I don't think we've done that.
Oh, Mark. Nice to meet you.
Mostly right now I'm thinking about holographic entanglement entropy, also trying to understand graviton corrections, so the holographic entanglement. That's what I'm talking about basics, if you're going to basics.
No, I'm not going to talk about this. I'm not talking about that anymore. I'm mostly thinking about like.
Yeah, I'm actually very interested in trying to understand trying to derive this
It doesn't matter. Yeah, because you know the general
Yes, a little bit. There's
this thing
something
that
also going
the runtime modular flow.
with Daniel Jeffries and so on. As Arvind, the sort of I just wanted to ground right on.
Yeah, you just have like
the actual but there's more problems there because it's singularity is not
Let me say what I was
off-shell, what's this delta function.
So
delta function singularity is like a local thing. So we're trying to do that very local
in holography we know that
Some sort of AES3.
is somewhat approximated by the area operator.
which is what we know the Worldsheet
And then we
and so invent a deformation that creates a conical emphasis in the target space.
generated by
The target space now is not.
and there is this
On
story
shell.
that it's like this one-sided restriction deficit, what we call
So just like this, for example, this creates like a boundary
Yeah.
wall, right? This, the analog of that going is to see, but you invent, you come up with something,
Yeah.
a deformation of the AES3.
Yeah.
And what I did once I will create a conical emphasis. Now, what is the understanding of this conical? Initially, we understand this conical term. In fact, if you look at this one thing, we give two different tricks, right? And one of them is that you add and subtract columns and stuff like that. Familiar, of course, with and the other one is the range method.
So it is actually
Right, where you actually write down a range, four-dimension two thing, which you don't know what it comes from.
Yeah.
But just a trick
Yeah.
to do the variation, you know what I mean?
Yeah, yeah,
Good, good. So it's not clear for us from a string theory Worldsheet perspective whether this sort of which interpretation
just like JD.
maybe turned out to be equivalent, right? And so I have some information. So one thing was and then what does it mean? Then a 1.5 function, no, so the torsion function of the background. This is the sort of thing we're trying to get
Yes,
sense
like,
of.
everything is just fixed by R.
Like integration over R, where the G, the two-dimensional
and you couple it
over
with
a manifold with like a cone.
Yeah.
But you want to write a regular cone, so you write some symmetric, right? What does it give you? Give you something like 4pi times data. What do you check is and you see here also normally this would be a delta function on the right-hand side. Because it's just right. So what? So if you compute this action in such a background and put the correct regularizations, you end up with something which is not a function on the right-hand side. This is the beginning loop with this in, and then this is the Einstein-Hilbert action. You integrate this with one dimension two stuff. You get a three-dimensional horizon, and you get the so what we would expect, hope to get, is that the integral over the Ricci scalar over some version of the regular will do some 4pi times the function deficit 4pi n.
So you can ask like what happens when you like look at the flow of this thing, and it turns out to be more complicated. So it's like it's some general.
And then you integrate over the entire target space and you get a co-dimension 2. That's what we hope to get. So you want to get this information on your worldsheet theory, which is ADS3, such that instead of getting the fields themselves, so like this R, this
But you need to somehow see the actual localized
right?
Only the two of them.
Only the which is because you just add addition and subtraction, right? That's what we want to get.
But this seems hard to find. You said you can do this by.
That's an information. That's the goal of this sort of magical definition that you introduce in the worldsheet. If the definition is correct,
Yeah.
so doing the integral on this background, instead of just getting generic R, we should get 4pi times the quantity.
I see.
Directly.
I see.
Right? So here, this is like background independent in a sense, that we just are, but we never really specify what the background is, right? The background is whatever the background is. This is the Ricci scalar or whatever the background is. But here, because you're forming ADS3, and then you're including a cone, and you're regularizing the cone somehow in a particular way, you want that your target space action integral over R, so you imagine your manifold is like R times some other, it gives you this formula. Right? And then from there, you can claim victory, right? But of course you want to make sense of exactly what strings mean, because now we have some sort of, there's some crazy stuff happening in the worldsheet. One of the things is you can think of multi-valuedness, right? Because the worldsheet operator will be multi-valued. Well, the strings will be multi-valued on the worldsheet, but also in the target space. Well, orbifolds are, like for example, orbifolds you have cones because the vertex, the fixed point of the orbifold. For example, like C1, C3. That will give you cone. But that's an on-shell. That's an on-shell background. That's not double crossing, right? Good. But then you can ask, how do we deal with this? Well, we have some twisted operators, and we make sense of this. And with twisted operators, we impose some locality conditions, which basically means that you have to close. I mean, you have here the crazy thing, because here the conical deficit is 2pi times 1 minus 1 over n, right? Here it is, so this is the conical deficit of the integer, right? Here